And we're rolling. Hi there, nerds. I'm Nibir, and welcome to the second video of the series on trigonometric integrals. And yeah, last video was pretty long. It was about 1 hour long, and I did not really realize that. I'm gonna try to make it short. That means you have to watch the previous video because I covered a lot of concepts that are going to be used in this one as well. So make sure you watch them because you might not get a few things if you don't. So do that and let me show you guys the screen. Otherwise, there will be no math, right? So we got the second video and we were done with the x squared plus a squared gang. And now we're going to move on over to x squared minus a squared gang. So again, we have similar structure of the integrals. Instead of the additions, pluses, we've got the minuses over there. So everything is the same. We're going to use similar concepts, similar trigonometric substitutions to solve for this one, to derive these ones. And again, as usual, try the examples out yourself and it's going to be amazing. So let us just move on over to the first member of the gang, that is this good fellow over here. So what do you see by looking at it? Is that it is one of the simpler ones to derive. You don't really need to use a trigonometric substitution. Of course, you can, I guess, but it's just going to make things difficult because, this is a known algebraic identity. It's not even trigonometric, it's algebraic identity. It's known, you know that some x minus a squared, that is, okay, I should not draw the thingy. This equals to x minus a, x plus a, and you know that it's absolutely true and absolutely correct. So why would you go about making things harder by putting in extra trigonometry and something like that? Even though it makes things easier, sure, geometry makes things easier, but we're going to do this a different way. We're going to do this by partial fraction decomposition. So if you're unfamiliar with the technique, you gotta do it. You gotta know it. Okay, just watch some other video and come back to this video after you know what it is, if you don't know already, or if you want me to make a video on it, then comment down below. I'll try my best to do that. So okay, I assume that you know how to do partial fraction decomposition, and then I'll move on with that mindset. Okay, so okay, partial fractions. So what does that mean? That means that we can represent any, oh my god, I erased it. Yeah, we can represent any fraction, polynomial fraction thingy into two different polynomial fraction thingy. And the two different polynomial fraction thingy have the denominators of the factors of the respected thingy over here. Okay, again, you gotta know what partial fraction decomposition is. I'll if you want me to, again, I'll try to make a video on it. Just you gotta comment down below if you want that. Okay, so all right, let's do it. Okay, so we can write this whole fraction, rational polynomial, you can say, like this. If you do the partial fraction, it's going to be some numerator a divided by x minus a, because that's one of the factors. Amazing. Plus b x plus a, because that's the other factor. So we gotta find a and b now. So how do you do that? Again, there's a pretty neat method called cover up method, and for that I need to actually rewrite this in this form. So okay, let me do that. X minus a, x plus a. So what the cover up method wants you to do is just pick one of the two fractions. I mean, it can be more than two, but in this case, pick any of the two fractions. Okay, I'll pick this one, all right? And I'll see for what values of x is this denominator going to be 0. For what values of x is this denominator going to be 0? And it's going to be a. So if x is not x but a, this is going to be 0, right? So what we're going to do is we're going to cover in this side, in left hand side, this term, which is the same as this one. We're just going to cover this one, right? Just cover this one and replace x's over here with a's, because this is where the denominator becomes 0. Okay, so if I say that, okay, this is a, then we have 1 over 2a over there, right? 1 over 2a. And that apparently is the value of a, because we chose this fraction, right? So that's the value of a. It's neat. It's something magical. I don't know. Again, so if you want me to just watch a black pen, red pen video, man. Yeah, he's amazing. So let's do this for B instead this time. So for B, we're going to do the same. We're going to cover up x plus a. Okay, x plus a. And before that, let us see what values of a, x makes this whole denominator 0. And that is going to be minus a. So, okay, let's cover up. Oh my God, I'm erasing this every time. So let's cover up this one. Let's just, okay, great. So we've covered up x plus a, and let's put x equals minus a this time. So if this is minus a, this whole thing is going to be minus 2a, right? So we're going to have minus 2a, and that is going to be our b. Great. So that's how the cover up method works. Again, yes, black pen, red pen has a nice video on that topic, that concept. So watch that and then find that out. So I'm gonna move this over here because for reference, and I'll just put a box, little box, great box, good box. Yeah, like that. Great, amazing. So this means that the whole integral this time, it's just this thing, right? Of course, it's that thing. Of course, it's this sign. And we have a to be 1 over 2a. So we can just factor it out. 1 over x minus a plus, not plus because we have a minus over here. So we're going to add minus 1 over 2a. And then we have x plus a over there times dx. This is how partial fraction decomposition works, okay? And we can see that this thing is common, so we can just factor it out and factor the whole thing out because a is just a constant. So again, we can do that. We can very well do that. Absolutely. We will check this. And of course, you should check this, right? You should check this. Okay. So we have inside the integral, we have x minus a minus x plus a over dx. All right. So we can separate these one as well. Thanks, integral rules. Thank you so much. Thank you being able to copy and paste. Yeah, amazing. This one is just that. Again, I should have done that in a different line because otherwise you forget what's being done, right? Oh man. I have to copy and paste again. But let's just copy and paste. Nothing else cognitive. So we have this one. Amazing. Again, this just looks like a simple u sub, and the integrand is going to be a natural logarithm. Okay. I'm just going to write it. Not going to worry too much about the u sub thingy. I can do this in my head. Okay, I'm gonna do this for this one because that one immediately follows what I mean. So okay, take u to be x minus a. Great. So x minus a, then du becomes dx because this one is a constant. If you take the derivative of it, it's 0. Again, for the derivative, this one's going to be 1. So du equals dx. And so this thing over here becomes 1 over u du, and that equals to the natural log, the absolute value of u. So amazing. We can cross that up here. I guess we will keep this over here. Yes, we can do that. And erase this. Great. So that means we just have 1 over 2a, and this is just being multiplied to this thing whole. Yes, and this one is natural log of x minus a minus we have the natural log of x plus a, and that is being done here. But again, if you use just simple logarithmic properties, this when we have a negative sign, we what we do is take a fraction of the natural logarithm function. So this is essentially 1 over 2a. Again, I forgot the plus c over here. Do not forget that. Okay, it's important. It's pretty important. So we have the natural log and the absolute value, and we're gonna put the first part over here, which is not negative this here, and this part which is negative. This is what I mean by negativeness. I'm not being rigorous enough, but I hope you know what I mean. So okay, this thing plus c. This is the final integrand of this gang member over here. So amazing. I hope this was clear enough. This is like different from what you'll see on from um, other gang members. I should say gang members. All right, so gang members, but and that's why it's like one of the outliers. You can say this like a mafia boss or something like that. I'm rambling over here. Let's do some problems. Okay, right. Absolutely. This one is amazing. This is a 9 over here, by the way. 9. So a 9. That's my dad. So let me pause a bit. All right. Post father and son interaction. We're back. Okay. So yeah. Let us move on with the question. The example. Simple. It's so simple. A is square root of 9, which is 3. So we're gonna have just putting in the formula, all right, 1 over 2a, which is going to be 3, because this is being squared, right? So, okay, 3 natural log of what did we have again? Shit, I forgot. Yeah, x minus ax. Yeah, completely. Sorry about that. Yeah, x minus 3, x plus 3, and c. And this we can replace with good old 6. 6. So this is the integrand. Amazing. Let's move on with the second one. Let's do it because it's amazing. It's interesting. It's amazing because we're gonna take a, not going to say it because you're gonna do it first. All right. So pause the video and try it yourself. Again, we're gonna solve it in 3, 2, 1. Let's do it. So we're gonna take a u sub here. That's going to be 3x plus 1 because we need this to be not like this, right? Okay, not like this. That means we're gonna have du equal to if you're 3x, then it's going to be just 3. So du will equal 3 dx. Amazing. That means dx is going to be du by 3. Okay, yeah, dx is going to be du by 3. All right, great. We're going to replace them both over here. 1 over u squared minus 16 and du over 3. Great. We can factor this 3 over here out. Integrals, you know. So, all right. 1 over 3, the integral of u squared minus 16 du. Again, we have the integral in the form that we want instead of this weird thingy. We know what to do now. We know the a because a is just square root of 16. That's 4, right? So it's going to be pretty easy. 1 over 2 times 4 times the natural log of, I did not forget it this time, x minus a. Again, this is 4. X plus a, that is 4. And plus c. Again, we can replace this 2 times 4 with good old 8. So I hope you got the example right, and we can actually move on to the next gang member, that is square root of x squared minus a squared. And yeah, that's that one. So here's we're gonna use the same trigonometric, our Pythagorean triangle substitution technique here. So if you're unfamiliar with what I'm talking about, you should watch the previous video. All of them require the same technique. So we're going to use that. I'm not going to elaborate too much, but we're still going to do it. All right. So let's do it. So here we know we can divide the whole thing by a squared, and that would give us a simpler looking polynomial. So let's do that first. Okay. We're going to focus with the square root. So x squared minus a squared. We're going to divide it everything by a squared and multiply everything by a squared because that will conserve the thingies. We can factor this a out, square rooting thingy, and these x's are going to be cancelled. So ultimately, after all the algebra, we're gonna be left with this nice thingy over here, and we can input that over the integral because these are the same things. And we know that a is just a constant, so it's going to get factored out in the integral. So a, we're gonna have the integral sign, and we're gonna have a good old square root x minus a etc etc dx. Right, don't forget the dx. Now this is crazy. We're gonna make not a substitution, not tangent of phi, but we're gonna make a some other substitution. But before that, let me draw a good old triangle, a right triangle. Because we love right triangles, don't we? Okay, this one. Okay, it is not a right triangle. This barely a right triangle, but okay, we'll take that approximation. Okay, so this is the right triangle, and here's what we're going to do. This whole thing looks very similar. You know, just think about the identities of how we do these substitutions. Okay, how we do these substitutions. It's thinking about the core trigonometric identity. You got your cosine square theta plus x square sine square theta, that one equals 1. We got 1 plus tan square theta equals secant square theta, that one. And we got the cotangent and cosecant one, that as well. You see that those are these have a similarity between them, something geometrical. You know that if this thing was secant, then whole thing would be a tangent. Yeah, it's weird. It's weird of how we come up with these geometrical thingies, but that's crazy, right? That's why math is beautiful. It's just crazy, plain old crazy. I don't know what else to say. It's just crazy and it's beautiful that way. So let us make this substitution. Let's take x by a to be the secant, not the tangent, but the secant of some arbitrary angle phi, and we're going to make this angle phi over here. Great. So if this is secant, that it's the reciprocal of the cosine. So a over x is cosine of phi. That will help us find out that this is a, this is x, and then automatically by the Pythagorean theorem, this is going to be x squared minus a squared. Okay, it's getting cut off. So x squared minus a squared. I'm gonna move it over to here. Okay, great. This is the simple substitution we made. Let me wipe this down because we're gonna need it, because we're gonna do some more substitution and solve for dx, because we're gonna need that. We're gonna move over to the phi mode, right? We're gonna change variables this time, so we're gonna find dx as well. So what's it going to be? X will equal a secant phi, then dx is going to be just the derivative of all thing. The constant will stay constant, but what's the derivative of secant of phi? That's secant of phi again times tangent of phi. Again, we're just doing d phi right here, so it's going to get cross multiplied over there. So these are the core substitutions we are making in this gang. So we're going to just put it over there, right? Just put this thing over there, and let me write it here. And great. So we got a, and we got our good old secant squared phi minus 1 times we got our a, again secant squared tangent, normal tangent, and we got our d phi because we're substituting for dx over here, excuse me. All right, so we know that this is just plain old tangent square x. Why? Because 1 plus tangent square phi equals secant square phi, right? We know that, absolutely. So this is going to be tangent square phi, and we're rooting it. So it's just going to be, no, just normal tangent, not squared, basically. All right, so this is going to be a. So that's the tangent. And we can factor this a out as well, to be honest. So a squared times secant times tangent d phi. Again, we'll have an interesting combination. We can simplify it even more. It's going to be a squared tangent squared phi secant phi d phi. Okay, the border. So this is the thing. And it looks weird. It looks like it's hard to solve, but it really isn't, because you can back substitute for tangent with, again, this one, the same identity. So we'll find the thingy in terms of our secant. So this equates to secant square phi minus 1 times secant x d phi. And that, in turn, whew, it's going to be a long one, equates to secant cube phi minus secant phi d phi. We can separate these out again. Let me copy it. Good old copy paste magic, right? We need that sometimes. We need that a lot of times in our life. I wonder where I will be, I will have, if I did not have the power of copying and pasting things. Yeah, I'm a programmer. Okay. So, as I said, we need to know certain functions, certain common integrals, and secant cube phi, secant cube phi, and secant phi. We need them. Again, as I said in the last video, let me know in the comments if you want them, if you want me to show you how to find the integral of these functions, and I'll gladly do it. So comment down below, along with your other queries and questions. So, but now we'll just plug in the answer for this one and go the good old rote memorization way. Oh man, I don't like it. I don't like rote memorization. I like finding things, but we gotta do what you gotta do, right? So this thing over here equates to 1 over 2. We got secant phi. As I said, this is going to be a long one. I hope you have your popcorns and stuff. I don't know. And the natural log of secant phi plus tangent phi. And then this one. Okay, let me mark them. All right, this one and this one. This one is going to be actually just natural log of secant phi plus tangent of phi, and close the bracket. And we can see that these two things are similar. So if we add them both, it's just going to be minus half natural log of this thing. So amazing. We know what to do. We can also bring in the a square over there. So amazing. I did take too much space, so I'll have to use the next page. Okay, we'll do that. We'll do that, surely. Okay, so a squared over 2 secant phi tangent of phi minus, not plus, because we're adding these things, minus half natural log of secant phi plus tangent phi, and do not forget the plus c. Yes, do not forget the plus c. I should have added this here as well. We got this thing over here, and with that, we can move over to this page. And also, you know what? Let's try. Yeah, okay. So we have this triangle, right? We can find the secant and the tangent using this and plug into this over here. So let us do that. What is the tangent of phi? What is the tangent of phi? That equals to this divided by this. So x squared minus a squared times a. And what is secant? We know we did the substitution. Secant phi is just x over phi. Sorry, x over a. And let me make that white. Great. So we're just supposed to make the substitution, and if you do that, I'm not going to make it any longer. It's just going to be this one. All right, just try to do it on your own right now. Okay, try to complete the rest of this derivation. Okay, so all right, let's do it. The whole integral, let's take it I, is going to be 1/2 x times x squared minus a squared minus, it's going to be a squared by 2 natural log of x plus a squared minus a squared by a and plus c. We are done. Yeah, we are done. Let's go. Damn, this is like absolutely super similar to the uh addition counterpart. It's just that they are differing by this plus sign, and the plus is right here. That's it. So they are super similar. It's really easy to memorize if you know either one of them. So this is the answer to this one. I mean, the integrand of this whole thingy. Wow. Okay, so let's move on over to do some examples. Again, I'm gonna make this super quick. Please try to do them on your own, and we're gonna stop. We're gonna no, no, start. We're gonna start in 3, 2, 1. All right. We know what a is. A squared is 16, so a is going to be 4. Great. So we can just plug and chug into the formula, or we can use our good old triangle and do the substitutions. Try to find them. You know, this thingy. We can do that. Of course we can. Of course, but it's going to take more time. So do that only if you do not remember the formula, or if you want to understand how the geometric thingy relates to our calculus world. So, okay, let's just plug and chug the formula for now. All right. So, okay, we know the A's. So the formula, just putting into the formula, is just going to be half x times the thing that will repeat itself again minus a squared, which is just 16 by 2 natural log of x plus, let me move that over up a bit, minus 16 divided by 4, close the absolute value, and boom, we have that. And we can replace this thing with good old 8. So great, we can delete this. Absolutely. So this is the answer to this integral. Similarly, we can move over to this one, and this one is a bit feisty. I think I forgot how to do it, man. Wow. Yeah, this one is a bit feisty because it does not use the normal thingy, but uses a part of it. So, it's going to be fun doing it, isn't it? So let us try to do it again. Feel free to pause the video right now and try to solve it. It's going to be amazing. Okay? So, all right, let's do it. So, what's it going to be? Can we do some division? Can we simplify this thing a bit? Or should we just do something else entirely? Like doing the substitution this time that we did here. Because as I said, when I was talking about noticing things, can we notice something? We can notice that if this x was secant, then this whole thing would have been a tangent. Things would have been much easy. Can we notice that? Can we see the pattern here? Whenever this is something squared minus 1, can we make the something into a secant? That's the thing we're talking about. That's the intuition we need. So we're going to substitute x to be secant of some arbitrary, let's say, angle. Let's take theta this time. No, not theta. Phi is our best friend. Okay. what if we do that? Okay. What if we do that? Then the dx is going to be just secant squared. Sorry, not squared. Normal secant times d phi. Great. Amazing. Makes our life much easier. So we can substitute x for secant of phi. Let's try that. Let's do that. This is going to be secant squared phi minus 1. And here is going to be secant phi. And dx is going to be secant phi tangent phi d phi. Great. Okay, amazing. And right away, we can see that these are going to get cancelled. And this is nothing but another tangent of phi. So we'll have tangent squared phi d phi as our integrand. But we're not done yet. We are not done yet because we can simplify this even further. Why? Because guys, see this. This is secant squared phi minus 1 d phi. This tangent equates this because of the identity, So we can do more things. All right. We can separate this out. Secant square phi d phi minus 1 d phi, which is just d phi, because you don't need to write d phi. Sorry, like 1 d phi. And we can find the end. This is like we can find the antiderivative of this thingy, we can find the antiderivative of this thing, and it's going to be tangent, just tangent. Why? Again, because for some x, tangent phi equates to secant squared x. So if you take derivative of both of these things in terms of x, these are going to get cancelled out. They're sort of like inverse thingies, right? And this thing is going to be equal to tangent of x. So great insight. Amazing. This is fundamental thingies. Yeah, this is very fundamental. You gotta know how to handle with this one. So it's going to be secant tangent of phi, and this is just minus phi. Okay, just minus phi. Great. Plus c. We don't forget the plus c's over here, do we? Great. So we're still in the phi mode. We gotta get back to x mode. So here's what we did. We picked x's to be secant of x. So what's it going to be? What's x going to be? What's phi is going to be? Phi is going to be reverse of this thing, Oh, okay. For the first time, I am stuck in a loophole. All right. Let's figure this out. Because I did not do it before the lecture, so I'm doing it live. So it's live problem solving mode. All right. So x, normal phi is just arc secant, if there's such a thing, arc secant of x. Great. And tangent. We can just make a triangle. Yes. Whenever there is some angle, we can just make a triangle and find tangent that way. Amazing insight. So let us take this triangle over here. And we're gonna have to do some changes, of course. We're gonna have to change the sides because there's not really a. We don't have any a's in this equation. So let's wipe these. And we know that we took x to be secant of phi, right? Which is the reciprocal of cosine. So cosine of phi is going to be 1 over x. Great. That means we know that the base is this one, the hypotenuse is this one. So this thing is going to be x squared minus 1. So that means tangent of phi. Okay, I'm supposed to be writing here. Okay. So that means tangent of phi equals to this thing perpendicular over base. So that is just this thing. And what is phi? Phi is arcsecant of thingy, or you can say arc cosine or cosine inverse of 1 over x, because just this thing, this is much better than arc secant. Who uses arc secant? Right, arc cosine. So that's it. That's it. That's our answer right there. Using not the formula. I know I threw a curveball here, right? Yeah, for myself as well. No formulas here. Just plain old substitution. That's how life works. It throws curve balls at you. So okay. Awesome. We should be celebrating right now because we found the integrand of this weird thingy. We did not use the formula. We just use what we did for the derivation, trigonometric substitution. This is why it's called trigonometric integrals, bro. Yeah. So this is the answer. Amazing. Let's let's move on to the next gang member. All right. Again, this is very, very similar to the, remember the X counterpart of this one? It's just the same. I don't think I want to do the derivation, but it's really, really simple. It's just okay. Let me see my notes. If there's anything useful to talk, it's just the same. Okay, it's just the same. Okay, let us do it. Let us make the same algebraic manipulations. We're gonna take the polynomial for now, divided by x, sorry, a. So we're gonna be left with this thing over here, and we're gonna integrate that, right? So let me just write that completely here. Okay, so integrating, we'll have 1 over a outside because this thing, again, I'm just using the same thing we did for this derivation, this thingy, taking the a out like this. So the same concepts applying over here. All right, so again we'll have x over a squared minus 1 dx. Great. And that, if we're gonna do some substitution. X over a is going to be secant phi, just like the other one, this part, this derivation, previous derivation. So dx is going to be a secant phi tangent of phi d phi. Amazing. We're going to substitute this back into our equation. Right, let's do it. 1 over a times, this is going to be secant squared phi minus 1, and dx is going to be a secant phi tangent phi d phi. Okay, too many phi's, but we love phi's. Phi's are great. And this a is going to get factored out and effectively get cancelled because we have a in the denominator as well. And this is just secant, sorry, this is a tangent squared, which is being rooted out, this root. So it's going to be another tangent. So eventually we'll have a tangent war, and they are going to get cancelled. All right, they are going to get immediately cancelled beautifully. We love cancelling things out, definitely. And we'll be left with a simple secant phi d phi, which equates to natural log of secant phi plus tangent of phi and a nice old plus c. Great. But we're not done yet because we're still in the phi mode. We need to be in the x mode. So what is our secant? We know that because we took this one. And what was our tangent? We need to take our good old previous triangle. Yeah, we found the tangent to be this one. Screw nose, no screws. Square root x squared minus a squared by a. So we're gonna do that. We're gonna do the same, and it's going to be natural log of, finally, after doing the algebraic manipulations, it's going to be x plus, yeah, okay, x plus this thing because we have addition, and we'll have a minus over here over a. All right, amazing. This is the integrand of this one. Again, you'll notice some parallel thingies, similarities between the plus and the minus counterparts. This is just the same. The plus counterpart has a literal plus in it, so that's the only difference. Again, it's the younger sibling of this one over here, our previous one, because this is the only part that this one has, right? These are the same. So it's really going to be easy to remember, especially when you do these examples. So let us do this. Okay, what do you know about this one? Again, pause, try it yourself. Okay, right. So A is going to be 9 because 1881 is 9 squared. All right, so can we just put this into the formula and be done with it? Absolutely. But can we also do a trig substitution? Absolutely. It's going to take some time, take some mental effort, but you will know exactly what it means, how it happens. So you should do that sometimes, I'm not going to do it because it's going to make the video more longer, and the longer it goes, the less people view. But okay, either way, let's do it. Okay, it's going to be natural log of x plus the thing that repeats itself. You don't even need to worry about the thingies, and just write 9 plus c and you're done completely. So absolutely, you crushed this one, but this one is a bit more interesting. So I just try it. Okay, just try it, and let's see if you can do it. So we're gonna try in 3, 2, 1. I hope you've tried it. I hope you have succeeded even. So let's do it the good old way. Again, we don't know. We don't have a good way of solving this. We can divide it out. We can divide the whole thing by 9 and factoring this thing out. For sure, we can do that. And we did that in one of the examples in the previous video. We did that, the same thing. We can also do a simple u substitution. We're going to define u as 3x because this is just 3x squared. So we're going to take a u sub of 3x. Du is going to be 3dx. So dx is going to be du by 3. Great. So amazing. Life is good. We're going to substitute back into the integral, which is going to be 1 over u squared minus 16 and times du by 3. This 3 will go out, factor, all right? Factor it out. We're going to factor it out. Normal integral rules, and we're going to have a good expression over here. Really good looking expression, because we know we can solve this one. This one is a squared and this one is x, but this is not x, this is u. Okay, do not get confused. I'm just making things easy. So we're going to have 1 over 3, and then over here we're going to have our natural log of u plus this thing, not x, u squared minus 16. And over here we have a 4 because this is 4 squared. And we're going to close this thingy, add a constant, and we are done. But are we? We are not, because we're still in the u mode. We're going to have to get back to the x mode. So, all right, 1 over 3 natural log. What was u again? It was 3x. So 3x plus, this was the original function, which was 9x squared minus 16 over 4, close the absolute one, and plus c. And now we are done with the last example for today. Phew, we are done with the x minus x squared minus 1 gang. I hope you've learned something. All right. Okay, great. And again, as always, we have a problem set PDF linked in the description. It will have problems and you should go and solve them out, because that's how you learn things better. You need more problems, basically more and more and more and more problems. And also we have the next video, which is on a squared minus x squared integral type. So click there in the video and you'll find the right way. Also, join my Discord server. We have a lot of people studying over there. We have accountability channels. We have study guides, and overall, you'll get to meet new friends and meet like-minded people, which is what we want, right? Which is what we want. Yeah, absolutely. Again, hit the subscribe button, hit the like button, whatever. If you like this video, that is not forcing you. Again, if you have any questions, any queries, just comment down in the comment box. Oh my god, my English is not English. Either way, I hope you have learned something from this video. Again, if I made any error, you're just free to just demolish me. Just do everything. Just point that out. Please, please, please just point that out, because I can make mistakes and I do my best to rectify them in the description or comment, whatever. So please do that. And as always, take care of yourself. Do more integrals, do more calculus, more math, and stay frosty. All right.